This portion of the week's lecture covers equivalent loads. First, we will go over the definitions of some important terms in this lecture. A load refers to a weight or pressure caused by something or someone that is applied onto another object. There are different types of loads, but we will be focusing mainly on two categories. A uniformly distributed load, or in short form UDL, refers to a load that is evenly distributed, or in other words, spread out over the entirety of the structure. An example would be a rectangular load. A distributed load, or in short form DL, refers to a load that is distributed, or in other words, spread out over the entirety of the structure, but not necessarily evenly. An example would be a right triangular load. A point load, which means a load that is concentrated at and applied only to a single point of a structure. We will now apply these concepts to a couple examples. We will first look at a rectangular UDL, or uniformly distributed load. Ask yourself, what point load can this be replaced by, and where this force should be located? In the diagram, we are given that the distance from the left support of the beam, labeled as point A, is 8 meters from the left end of the load. We also know that the load is 6 meters in length, and the right end of the load is 6 meters from the right beam support. It is shown that the UDL has a downwards force of 2 kilonewtons per meter along the entire 6-meter length. Also, recall the coordinate system with positive forces acting upwards and to the right, and positive moments rotating counterclockwise. Next, to create a point load that is equivalent to the UDL, which we will call F equiv, we will multiply the distributed force of -2 kilonewtons per meter, negative because it is acting in a downwards direction, with the length of the UDL of 6 meters. This gives us an answer of -12 kilonewtons. To summarize, the magnitude of the point load F equiv will be equal to the total force, or the area under the UDL. Now, to find the location of the point force, we will need to determine the centroid of the original UDL. The definition of the centroid of a uniformly dense geometric body is where the center of mass is located. The center of mass is a single point that represents the mean or average position of the entire object. Note that this is not necessarily the exact middle of every object. We will now calculate where the centroid is as a distance represented by the variable d from the point A in the diagram. For a rectangular load, the centroid is at the exact middle. We need to add together the length of the beam from point A to the left end of the UDL, which is 8 meters, with the distance from the end of the UDL to the middle, which is half of the entire 6 meters. This gives us a final answer of 11 meters. Note from this example that the entire length of the beam is not necessarily needed when completing the calculations. The second example we will explore is a triangular load, or triangular DL. Consider the same question as before. What point load can the triangular load be replaced by, and where should it be located? In the diagram, we are given that the distance from the left support of the beam, labeled as point A, is 8 meters from the left end of the load. We also know that the load is 6 meters in length, and the right end of the load is 6 meters from the right beam support. It is shown that the DL has a downwards force of 0 to 3 kilonewtons per meter along the 6-meter length from left to right. Also, recall the coordinate system with positive forces acting upwards and to the right, and positive moments rotating counterclockwise. For a triangular DL, the magnitude of the point load, which we will call F equiv, is equal to the total force, or area under the DL. Recall that the area of a triangle is 1/2 times base times height. So, to create a point load that is equivalent to the DL, we will multiply the distributed force of -3 kilonewtons per meter. Negative because it is acting in a downwards direction with the length of the dl of 6 meters. But since we are dealing with the triangle, we must multiply the entirety by 1/2. This gives us an answer of -9 kilonewtons. Same as the example before, to find the location of the point force, we will need to determine the centroid of the original dl. Remember that the centroid is where the center of mass is located. Different from a rectangle where the centroid is in the middle of the object, the centroid of a right triangle is distributed by thirds as shown below. So, to calculate the centroid as the distance represented by the variable d from point A in the diagram, we will need to add together the length of the beam from point A to the left end of the dl, which is 8 meters, with the distance from the end of the dl to the centroid of the right triangle, which in this case is 2/3 multiplied by the total length of 6 meters. This gives us a final answer of 12 meters. We will consider an alternate scenario with the same right triangle and the same distances and forces, but add a weight to the beam. We will assume that the beam itself generates a downward load of 5 kilonewtons and it acts only at the centroid of the beam. With these conditions, now determine what is the magnitude of the point load, which consists of F equiv calculated previously and the beam weight. Pause the video here to try it for yourself. As from before, we will multiply the distributed force of -3 kilonewtons per meter with the length of the dl of 6 meters, and since we are dealing with the triangle, we must multiply the entirety by 1/2. This time, we will also add the weight of the beam, and the answer comes out to be -14 kilonewtons. Finally, we will calculate the location at which the point load must act. Different from before, this time we will be using conservation of momentum or balance of moments equation. We need to add together the moment produced by the dl about point A, which is -9 kilonewtons times 12 meters, from the calculations previously, with the moment produced by the weight of the beam itself about point A, which is -5 kilonewtons times 10 meters, where 10 meters is half the length of the entire beam. We will set this equal to -14 kilonewtons, the new point load, times the unknown distance, which we will call d2. Rearranging this equation, we get an answer of 11.3 meters. In summary, we explored different kinds of loads in this lesson. We looked at uniformly distributed loads as well as distributed but not uniform loads. We applied the theory to 2 separate examples, one for a rectangular load and one triangular load. To conclude, let us look at these 2 real-life examples. The one on the left is a flat roof with a snow load that can represent a rectangular uniformly distributed load. The one on the right is also half of a snow-covered roof that represents a right triangular distributed load.